Looking back at the question posed in part 1, which of these two options would you rather receive? You might have an intuitive feel for which one is the better choice, and that's great if you do. But how can we quantify these options? How can we get to the point where we can say option A is worth X dollars and option B is worth Y dollars? We would need to do some time value money computations. Let's first define the basic essential components of time value money. I like to think of things in terms of timelines, so we'll put that in first. The first component is the present value, which represents money earlier on the timeline. This could be like something you'd receive or pay today. Next is the future value, which represents money that appears later on the timeline, in the future. We have an interest rate that functions as the exchange rate between money at different time periods. The interest rate goes by different names depending on the context of the situation. Sometimes it's called the discount rate, the required return, opportunity cost, cost of capital. Again, the wording usually depends on the scenario, but you should be able to identify the interest rate when you see it, no matter the terminology. The last component we need here is time, which is going to represent how long interest is going to be earned or paid. Let's get started with a very simple type of investment, simple interest. With simple interest, interest is only paid or earned on the principal investment. That is, the amount you put in or the amount you owe. We can compute the interest by multiplying the interest rate by the principal. Let's do an example. Say we deposit $1,000 today into an account that pays simple interest and we let it sit there for 2 years. If the interest rate is 6% per year, how much is going to be in the account at the end of the second year? After 1 year, we had earned $60 in interest, bringing our account balance to $1,060. After 2 years, we'll earn another $60 in interest, bringing our final account balance up to $1,120. We call this $1,120 the future value with simple interest. Now let's work another type of problem with another type of account, one that pays compound interest instead of just simple interest. With compound interest, interest is paid both on the principal invested and on any interest that's been paid in the past. We can do another example to illustrate how this is going to work. So assume we deposit $1,000 today into an account that pays compound interest. As before, we let the money sit in the account for 2 years with an interest rate of 6% per year. After 1 year, we'll earn $60 in interest, bringing our account balance up to $1,060. But in the second year, we earn $63.60 in interest. That's 6% on the $1,000 principal, which is $60, plus 6% interest on the $60 we earned in the previous year. That's where the additional $3.60 comes from. Putting it all together, our final account balance is $1,123.60. And we'll call this value the future value with compound interest. If we compare the future values with simple and compound interest, we see that the compound account will be $3.60 bigger. Well, where did this extra $3.60 come from? It comes from earning interest on interest in the compound account. We saw that in the second year, we earned interest on the interest from the first year. That gave us an additional $3.60. If we let the money stay in the account for another year, we would earn interest on this $3.60 as well. The interest just keeps on accumulating. That's what people mean when they say your money can work for you. I want to come up with a general formula that we can use to figure out what any account will grow to in the future. So let's try to break it up here and break down the example we just did. In the example, how much did we have after 1 year? We had $1,060. That is the $1,000 we started with plus $60 in interest. I can factor out the $1,000 to express the $1,060 as 1,000 times 1 plus 0.06. Now let's move to the second year. We end the second year with $1,123.60. How did we get that? Well, we start that year with $1,060. That's our principal. Then we earn interest of $63.20 in the second year. Adding the interest and principal portions together, we get the $1,123.60 we found previously. Now that's a messy expression, so I want to clean it up a bit. Combining like terms, I end with 1,000 times 1 plus 0.06 raised to the second power as our future value. That gets us to the 1,123.60 we have in the account after 2 years. Just staring at this expression, some of the numbers should seem familiar. What is $1,000? Well, that's what we started with. And what is the 0.06? That's the interest rate. And what is the 2? That's the number of years we're going to be invested. So let's take that format and turn it into a general formula to find a future value. We can say that future value equals present value times 1 plus the interest rate raised to the number of time periods invested. Present value here represents what we started with, and future value is what we end with. Bringing in the information from the previous problem, we can see that we end up with the correct result. The future value is 1,123.60. We can mess around with the formula to see how things will change if the variables change. For example, what if we invested for 5 years instead of just 2? In that case, we would change the n in the formula and the future value would grow to 1338. If we deposited $5,000 instead of just $1,000, we would replace the PV in the formula. If the interest rate was 10% instead of just 6%, we'd replace the I in the formula. The effects of compounding are very apparent when we look at investments for longer periods of time. Take this for example. Imagine that you had a relative long ago, maybe a great-great-great-grandfather, and he deposited $10 into an account 200 years ago that pays 6% interest per year. How much money would be in that account today, 200 years later? We can apply the future value formula that we just derived. We started with $10, so that's our present value. The interest rate is 6%, so that's our I. And the money was invested for 200 years. That's our N. Putting it all together, we see that the future value is over $1.1 million. That small $10 investment grew to over $1 million. Now let's imagine the same scenario, but instead of your relative putting money into a compound interest account, he made the mistake of putting it into a simple interest account. Let's figure out how big of a mistake that was. We can compute the amount of interest received each year by multiplying the $10 principal by the interest rate. He would get 60 cents each year. And remember, this is simple interest, so that amount does not change. So the total amount of interest earned over the entire 200 years is $120. Add that $120 to the $10 you started with, and the account will grow to $130. That would be the future value with simple interest. What accounts for the dramatic differences in the size of these two accounts? It's the effect of compounding. With compound interest, we can earn interest on interest. We can see here in the early periods, the difference in the size of the accounts isn't that great. It's only after time that the effects of interest really start to take hold and cause the compound account to grow much more rapidly. And we can see that it is indeed the effect of interest that's causing this. We can see that in the first few years, the simple and compound account paid pretty much the same interest each year. But as time goes on, those differences get greater and greater. In the final year, the simple interest account paid its usual 60 cents in interest, while the compound account paid $63,000 in interest. This should give you some insights about saving for retirement, right? It's important to get started early so that the effects of interest can work for you. In reality, it's actually pretty rare to find any accounts which pay simple interest nowadays. So for this class, assume that we're dealing with compound interest unless I state otherwise. So far, we've been going forward in time by computing future values. Why can't we go backwards? Well, we can. We can just as easily find the present value of something as we can find the future value of something. We call the process of computing the present value discounting, as opposed to compounding for future values. And discounting is the key to computing the values of stocks, bonds, and other investments. For future value, we start with some amount today and see what it's going to grow to in the future. For present value, we have something in the future and try to determine what that is worth today. And we can simply rearrange the future value formula to get an expression to solve for present value. The present value is equal to the future value divided by 1 plus the interest rate raised to the n power. Let's do an example. Let's say you want to have $20,000 in your savings account 5 years from now. If the interest rate is 5% per year, how much will it take? How much will you need to deposit today to make that happen? If I drew this on a timeline, it's going to look like this. We want to have $10,000 in 5 years, and we want to move backwards in time to see what we have to start with to reach that goal. Breaking out the components of the problem, our future value will be $10,000. That's how much we want in the future. The interest rate's 5% and will be invested for 5 years, and we want to find the present value. Plugging this in to the formula we get $7,835. That's our present value. It's important to note that these two values are equivalent. They just have different time units. Year $0 versus year $5. It's just as if we're comparing dollars and yen. Even though they look different, $7,835 today is equivalent to $10,000 in 5 years. If someone asks you which would you prefer to have, your answer should be, it doesn't matter. You would be indifferent because they are equal. Let's do another example. An investment advisor offers a product that will pay you $200,000 2 years from now. If the interest rate is 3%, what is the value today? 20 years from now. We can set up the timeline and see what $200,000 will be. We'll see that that's our future value. And we want to find out the value today, the present value. Putting it in our formula, we get a present value of $110,375. That's how much you should be willing to pay today for the product. Just as before, these are equivalent values. If the interest rate is 3%, $110,000 today is the same as getting $200,000 in 20 years. You might have noticed that there's 4 variables in this equation: FV, PV, I, and N. We've solved for FV and PV so far, and there's nothing stopping us from solving for the other two. So let's do that. Let's first solve for I, the interest rate. Solving for I can be useful because it can tell us the implied interest rate or implied rate of return on an investment. We can start with the future value formula and rearrange a bit and get this expression for I. Let's do a quick example. Say you're considering putting your money in an investment that's going to give you $1,200 in 5 years if you invest $1,000 today. What is the implied interest rate on this investment? You'll get the $1,200 in the future, so that's our future value. You pay $1,000 today, so that's the present value. And we'll invest for 5 years, so that's N. All that remains is the interest rate I. Solving for I, we get an interest rate of 3.71% per year. This information could be handy if you're trying to compare potential investment opportunities. If you find a similar investment opportunity that offers a rate of 5%, you might want to go for that one. So this allows you to compare. The final variable in the equation is N, time. Let's go ahead and solve for that. Again, we can rearrange our general future value formula and get the expression that we see here. Let's do an example to see how this information can be useful. Assume you deposit $10,000 into an account that pays interest of 6% per year, and you want to know how long you have to wait until your deposit triples in value to $30,000. Putting our information into the formula, we get, for N, we get 18.85 years. That is, if you invested $10,000 today, in 18.85 years, you would have exactly $30,000. So that's it. That's the basics of time value money. There's going to be a few more complexities that we'll add in the future videos, but the main concept will remain the same. There's a relationship between money and time that must be accounted for.